we'll look at optimization problems. So here are some guidelines. Step 0 would be to read the problem, and you'll know it's an optimization word problem if you are asked to maximize or minimize a quantity. Step 1, you could make a sketch and find a formula for the quantity you want to maximize or minimize. Step 2, reduce the formula to one variable because you want to take the derivative of it, and also find the possible domain. Step 3, optimize. So you could use the technique absolute extrema over a closed domain, or if you only have one critical value on the domain, you could use the first derivative test. The first derivative test determines if your critical value is a local max or local min, but if you only have one critical value on the domain, then it will be an absolute max or absolute min. Step 4, answer the question that was asked in the word problem. Example A. By cutting equal squares from each corner of a 24-inch by 36-inch piece of cardboard and folding up the side, you can make a box with an open top. Find the dimensions of the box that maximize the volume. So this is an optimization problem where we want to maximize the volume of a box. So here's a sketch of the piece of cardboard that's 24 inches by 36 inches. And here in yellow are the little squares, length x by x, that will be cut out after we can fold up the box along these green lines. So after we fold up the flaps, we'll have a box with length 36 minus 2x, height x, and width 24 minus 2x. So we want to find the volume and maximize it, and the volume will be the length times the width times the height. So here the formula for V is length times width times height, which is 36 minus 2x times 24 minus 2x times x. So here on the side, I factored out 2 from 36 minus 2x. It will be 2 times 18 minus x. And from 24 minus 2x, I factored out 2, so it's 2 times 12 minus x. Since the sides of the box must be greater than or equal to 0, this will restrict the domain. So here x must be greater than or equal to 0. Also 2 times 18 minus x must be greater than or equal to 0. So 18 minus x must be greater than or equal to 0. And x must be less than or equal to 18. And also the other side, 2 times 12 minus x must also be greater than or equal to 0. So x must be greater than or equal to 0, but less than or equal to 12. So the domain is from 0 to 12. So we'll want to maximize the volume of the box on the domain 0 to 12. So 2 times 2 will be 4, and I'll bring the x in the front. And after, I will FOIL out these terms, 12 minus x times 18 minus x. So here we're multiplying it out so we can take the derivative of the polynomial. So you can check when we multiply out, we have 4x times 216 minus 30x plus x squared. And then we can take the derivative of 4 times x cubed minus 30x squared plus 216x. So here we have the volume, then we can take the derivative v prime. We'll keep the constant 4, take the derivative of x cubed, it will be 3x squared. The derivative of minus 30x squared will be minus 60x, and the derivative of 216x will just be 216. This we can set to 0 and solve for the critical values. It's up to you if you want to take out the 3 from each of the terms, then we'll have 12 in front. So then we can use the quadratic formula with x squared minus 20x plus 72, where a is 1, b is minus 20, and c is 72. So here we have two zeros. x1 is 4.7, and x2 is 15.3. Since 15.3 is outside of the possible domain, the only critical value we have is x is equal to 4.7. Next we will optimize. We'll use the method of absolute extrema on the closed interval 0 to 12. It's up to you. If you want to use the first derivative test, you could also use that. Here we'll be checking the value of the volume function at the endpoints and at the critical point. So you can check these values. V of 0 will be 0, V of 12 will also be 0, and V of 4.7 is 1825.3. So since that is the largest value for the volume, x is equal to 4.7 maximizes V. So finally, we'll just answer the question. which was to find the dimensions of the box that has the maximum volume. 4.7 inches by 14.6 inches by 26.6 inches. In the next example, a cylindrical can must hold 250 milliliters of liquid. Find the radius of the can that minimizes the metal used to make the can. So here's a sketch of the can. It has radius r and height h. We want to minimize the metal used to make the can, so we will minimize the surface area of the can. The surface area of the can will include the top and the bottom, so 2 times pi r squared. And then you have the side of the can, which has height h and length 2 pi r. So the area of the sides will be 2 pi r times h. So we will use the constraint from the problem. The volume of the can will be pi r squared times h, and that from the problem is 250 milliliters or centimeters cubed. Then we can rewrite h in terms of r. H will be 250 divided by pi r squared. Here we can plug the height h into the formula, and then we will have the area A as a function of r. So here we just plugged in h, and after we can simplify, A as a function of r is 2 pi r squared plus 500 over r. So now it's a function of one variable r, so we can take the derivative with respect to r. So we can look at the domain for the area. In this case, r must be greater than 0. Also, h must be greater than 0. In terms of r, h is 250 over pi r squared, which must be greater than 0. And this is true for all r. So the domain will go from 0 to infinity. And since this interval is not closed, we'll use the first derivative test instead of the absolute extrema when we optimize. So our area function is 2 pi r squared plus 500 r to the minus 1. When we take the derivative, 2 pi times 2r, which is 4 pi r, and the derivative of 500 r to the minus 1 is 500 negative r to the minus 2, which I'll rewrite as minus 500 over r squared. So we'll want to find the critical values. This is where the derivative is equal to 0 or where it does not exist. Here I made a common denominator over r squared, but it's up to you if you want to do that. So a prime will not exist when the denominator is 0. That's when r is equal to 0, but r is equal to 0 is not in the domain, so we will not include it. Next we can solve for when a prime is 0, that's when the top is 0. So when 4 pi r cubed minus 500 is equal to 0. So we can bring the minus 500 to the right side of the equation. Then we'll have 4 pi r cubed is equal to 500. After we can divide both sides by 4 pi, then we have r cubed is equal to 500 over 4 pi. And we can take the cube root to solve for r. And we can cancel the common factor of 4 in the top and bottom. So we have the cube root of 125 over pi. So you can check that the critical value will be 5 over cube root of pi, which is around 3.41 centimeters. Here we'll use the first derivative test to optimize since we have one critical value on the domain and also we don't have a closed interval. So for the first derivative test, I'm checking the value of a prime to the left and right of the critical value 3.41. If you choose a value for r that is less than 3.41, you will see that you get negative values for a prime, which means that the function a is decreasing on that interval. And for values of r that are greater than 3.41, the value of a prime is positive, so we know that the function is increasing on that interval. So since we're changing from decreasing to increasing, at r is equal to 3.41, we have a local min. And since we have only one critical value on the domain, that means that our local min is an absolute min. So you can use any values you like to the left and right of r is equal to 3.41 to check the sign of the first derivative. Here, just as an example, I took a prime of 1, and that gave negative value, so that's why we wrote negative to the left of 3.41. And then I chose the value 4, that gave positive 19, so that's why it's positive to the right of 3.41. But you can choose any values that you like to show this. So now that we've shown we have an absolute min, we can just answer the question. So here we found that the radius, cube root 125 over pi, or around 3.41 centimeters, minimizes the surface area of the can.